Welcome to this explainer. Today, we're going to unpack the fascinating science and the everyday impact behind one of the world's oldest, yet honestly perhaps most misunderstood energy sources. When you think of green energy, your mind probably jumps straight to giant wind turbines or vast fields of solar panels. But today, we're exploring an energy powerhouse that comes straight from the earth and straight from your garbage can. All right, let's kick things off with a question that might just flip everything you thought you knew about green energy in America completely upside down. Seriously, take a second and think about it. What actually powers half of all renewable energy in the United States? Well, surprise, it isn't wind. And no, it's not solar either. The answer is biomass. I know, right? It's this incredibly surprising source that quietly accounts for roughly half of all the renewable energy we consume in the United States. It's an absolutely massive part of our energy infrastructure, operating right under our noses.
So here's our agenda for today's explainer. We'll start with what is biomass energy, then look at converting biomass to fuel, explore liquid biofuels for transportation, check out generating heat and electricity, and finally look at energy from municipal waste. Let's get right into it.
Section 1. What is biomass energy, the organic power source?
Okay, so by definition, biomass is an organic renewable energy, and we source it from things like agriculture, forests, dedicated energy crops, algae, and believe it or not, even the waste streaming right out of our cities and industries. It's considered renewable because, despite the time it takes to grow crops and trees, we can literally always just plant more to replenish the supply.
Now, when you actually break down where this biomass comes from, it's kind of surprising. You've probably heard a ton about corn whenever biofuels get brought up, right? But look at this. The vast majority of our biomass feedstocks actually come from crop residues at 31%, perennial grasses at 28%, and forest resources right behind at 27%. Corn, it actually makes up a surprisingly tiny 6% slice of the whole pie.
Moving on to Section 2, converting biomass to fuel. The science of transformation.
So how do we actually get the energy out of these plants, trees, and residues? I mean, you can't exactly shove a bunch of wheat straw into your car's gas tank, right? Well, scientists basically use two primary ways to convert this raw stuff into usable fuel. First up is biochemical conversion. This is where we use enzymes and microorganisms as biocatalysts to break down carbohydrates into sugars, and then yeast and bacteria ferment those sugars into products like ethanol. Honestly, it's pretty much the exact same basic science used in brewing beer. Then we have thermochemical conversion. This one uses extreme heat, usually in an environment starved of oxygen, along with chemical catalysts to break down the biomass. A great example of this is a process called pyrolysis.
Which brings us to Section 3, liquid biofuels for transportation, powering our vehicles.
Now, what do all those complex chemical processes actually give us for our vehicles? Basically, three big products. First, there's ethanol. This comes mainly from starches like corn here in the US or sugar beets down in Brazil, and it's heavily used as a gasoline additive. Second, we have biodiesel. This is produced from organically derived vegetable oils and animal fats, and it's used in compression diesel engines. And third, we've got biogas, which literally comes from decomposing biological waste and is mainly used for heating and generating electricity.
Let's zoom in on ethanol for a second. Now, ethanol is super common as an additive to improve engine emissions and bump up those octane numbers. But we've got to look at the numbers neutrally here. Its heating value is significantly lower than traditional fuel. We're talking 26,810 kilojoules per kilogram for ethanol, compared to a whopping 44,000 for gasoline. So what's the so what here? In practical terms, it just means a full tank of pure ethanol is going to get you a lot less mileage than a full tank of pure gasoline.
All right, on to Section 4, generating heat and electricity, the biopower grid.
So biomass isn't just about liquid fuels for our cars. It's actually heavily relied upon to generate heat and electricity for our homes and businesses too. We call this industry biopower. To put it in perspective, the US actually has about 10 gigawatts of installed biopower capacity. How do they pull that off? Mainly through three technologies. First is direct combustion, which is exactly what it sounds like, burning waste wood products in conventional boilers to generate steam for electricity. Then we've got co-firing. This is where power plants replace a portion of the fossil fuels in coal-fired boilers with biomass, which does a great job of reducing sulfur dioxide emissions. And finally, anaerobic digestion, which is this incredibly fascinating process where bacteria decompose organic matter without any oxygen to produce natural gas, mostly methane.
And that leads us perfectly into Section 5, Energy from Municipal Waste, the Power of Trash.
This is perhaps the most relatable part of our explainer, municipal solid waste, or, just everyday trash. Get this, according to EPA data from 2015, 4.48 pounds is the staggering amount of solid waste the average American produces every single day. Just imagine multiplying that by hundreds of millions of people, over 365 days. It is literally an ocean of waste.
But here's where it gets interesting. When we actually look at what makes up that daily mountain of trash, a massive opportunity reveals itself. Organic materials, stuff like paper, food scraps, and yard trimmings, actually make up more than half of it. And since these are biogenic materials, they represent a constantly renewing, absolutely massive potential energy resource.
So, with all this daily waste heading out of our neighborhoods, the EPA decided to research a really critical question about emissions and energy recovery. Simply put, when we're trying to recover energy from all this trash, is it better to burn it or is it better to bury it?
To figure this out, they compared two specific approaches side by side. The first is waste to energy, or WTE, which directly burns the trash to make steam to run an electrical turbine. The second is landfill gas to energy, or LFGTE. This one involves burying the waste and harvesting the methane biogas that naturally occurs as the trash breaks down anaerobically underground.
And the findings? Well, the research clearly concluded that direct burning, the WTE method, produces up to 10 times more electricity than burying it. 10 times! But that's not all. Burying the waste actually results in 2 to 6 times higher greenhouse gas emissions per unit of electricity produced compared to burning it. So, looking at it purely neutrally from an energy and emissions standpoint, the data definitely favors the burning facilities.
Now, to give you the complete objective picture here, there is a crucial caveat we have to mention. Even though biomass is totally renewable, the actual physical processes of growing, plowing, fertilizing, harvesting, transporting, and converting all that biomass into fuel, that still consumes fossil fuels. Because of this embedded fossil fuel consumption, the emission characteristics of biomass just aren't quite as perfectly clean as something like a solar panel or a wind turbine. Biomass is just an incredibly complex, vital part of our energy mix. It acts almost like a bridge between the natural carbon cycle and human ingenuity. So as we wrap up this explainer, I want to leave you with this provocative thought to ponder. As our chemical conversion technologies inevitably improve, will our green energy future rely more heavily on the dedicated crops we purposefully cultivate, or the literal daily trash we leave behind? Thanks so much for joining me today, and keep asking the big questions.